Section 7.3, Sum and Difference Identities. We start off with a couple of cosine identities. We've got the cosine sum and the cosine difference. I don't know that you'll have to remember this or memorize this, but it helps kind of to know the pattern. If I'm looking at a cosine, notice it goes cosine, cosine, sine, sine. Okay? We're talking about sum of two angles, A plus B. A is an angle and B is an angle. And then notice that if it's a cosine sum, then it's cosine, cosine minus sine, sine. You kind of start seeing these patterns pop out of these formulas. And it helps you to memorize it even if you're not really trying. Okay? So on the other one's a cosine difference. That means like an angle minus an angle. 45 minus 30 or something. Okay? And then you notice cosine, cosine plus sine, sine. That's kind of something to look for. Might help you to memorize even if you don't try. So example 1, find the exact value of cosine 15 degrees. Okay? We've never been able to find the exact value of cosine 15 degrees before. We've been able to plug it into our calculator, but we've never been able to use the chart to find cosine 15. Okay? But now we're going to be able to do that because we would be able to change 15 degrees into a difference problem. Okay? I could use numbers in the chart, numbers that I know, for instance, 45 degrees minus 30 degrees. Okay? I'm going to be using angles that I know about, 45 and 30, to figure out one that I didn't know was 15. Okay? Cosine 15 degrees equals cosine of 45 minus 30. Certainly you know that that's true. Okay? But using a formula, go back and look at our cosine difference formula. The cosine difference formula, that'd be 45 minus 30 there. Okay, so we've got cosine of the first one, 45, cosine of the second one, 30, plus sine of that 45, sine of that 30. Okay, it's just a pattern. Okay, it's just a pattern. And so the formula says cosine 45 degrees, cosine 30 degrees. Instead of minus, we say plus. Sine 45 degrees, sine 30 degrees. So it's a little bit complicated for our formula, but it's just a pattern, and we're going to just plug in things that we know. Okay, so look at the chart. You should be able to tell me really quickly, what's cosine 45 degrees? Square root of 2 over 2. And cosine 30, square root of 3 over 2. Plus sine 45, square root of 2 over 2, and sine 30 is 1/2. And so if we clean this up, okay, just clean up your fractions a little bit. We have square root of 6 plus the square root of 2. Both of those things we know over 2 times 2 is 4. Okay. The exact value, cosine 15 degrees, the square root of 6 plus square root of 2 over 4. Okay? Now the exact value of cosine 5 pi over 12 is a little bit harder. It's harder because we're not as good with radians and we're not as good with fractions, but it's still the exact same concept. Okay? If we're looking at cosine 5 pi over 12, what we want to do is make that into a sum or a difference. Okay? And so how we're going to do that, how I would like to do that, is you look at your angles in the chart. You got pi over 6, pi over 4, pi over 3, and pi over 2. It's very difficult to see how to make 5 pi over 12 out of that. Unless we do what we've done a lot in this class and talk about common denominators. Since my problem has a denominator 12, let's make all of these have a denominator 12. So I'm talking 2 pi over 12, and what would that be, times 3 would be 3 pi over 12. All I'm doing is times 2 over 2, times 3 over 3. I'm trying to get a denominator 12. Okay, times 4 over 4 would be 4 pi over 12, and times 6 over 6 would be 6 pi over 12. If you will look at a common denominator for our angles in the chart, it's not terribly difficult to see how to produce 5 pi over 12. If I just added those two, if I added 2 pi over 12 plus 3 pi over 12, that would equal 5 pi over 12. Okay? And so what I'm going to do is use a cosine sum. So I'm not going to say 2 pi over 12 and 3 pi over 12. I'm going to use the reduced versions, pi over 6 plus pi over 4. Okay? Pi over 6 plus pi over 4 is the same thing as 2 pi over 12 plus 3 pi over 12. And so you convert my problem, my cosine 5 pi over 12, into a sum cosine pi over 6 plus pi over 4, and then use your cosine sum formula. Cosine sum says cosine of the first one, cosine of the second one, minus sine of the first one, sine of the second one. So the hardest part for me is getting that fraction, getting that common denominator, finding that sum. So then cosine pi over 6, just look at your chart, that's square root of 3 over 2. Cosine pi over 4, square root of 2 over 2. Minus sine pi over 6 is 1/2. And sine pi over 4, that's square root of 2 over 2. Going straight from the chart. And so then cleaning up my fractions again, I've got the square root of 6 minus the square root of 2 all over 4. So cosine 5 pi over 12 equals that. Okay. Now in part C says find the exact value of cosine 87, cosine 93 minus sine 87, sine 93. It's the same thing, it's just backwards. Okay, it ought to be easier, but people kind of struggle with this one, I suppose. But look at which formula it is. Okay, did you notice the minus? Did you notice the minus in there? Okay, that would indicate that we're talking about a cosine sum. This must be a cosine sum formula, and so basically what we have is a sum. Cosine 87 plus 93. I used the exact same formula. I just used it backwards. I noticed this minus sign indicated that I was going to have a plus right here. So 87 plus 93 is what? 180? I'm looking at cosine 180 degrees and cosine 180 degrees. You should know this. Okay? 180 degrees puts us over here. I'm looking at the x coordinate of that point over there at 180 degrees. Here's 180 degrees. The x coordinate is -1. We talk about the cofunction identities, and we've actually seen these before. We've been quizzed on these and tested on these before. I think the formulas, though, are kind of complicated to look at. It looks a lot more intimidating than it actually is. When we talk about the cofunctions, sine 50 degrees equals cosine 40 degrees. We've talked about this, and I think you understand this. If I said tangent 20 degrees, that would equal cotangent 70 degrees. We know that cofunctions have this property that their angles are going to add up to 90. Cofunctions, angles add up to 90, and that's what all these formulas say. It's just kind of hard to look at. That's what they say, though. So secant 30 degrees equals cosecant 60 degrees. Okay, what are cofunctions? Sine and cosine. Tangent and cotangent, secant and cosecant. Those are cofunctions. And so when we look at example 2 down here, cotangent theta equals tangent 25. You probably should be able to do that in your head. It's going to be 65. Because we know those are cofunctions, and cofunctions arguments add up to 90. Theta plus 25 equals 90. We subtract the 25. Theta equals 65 degrees. I think you should probably be able to do that in your head, though. Part B, same thing. We're still using cofunction identity. Sine theta equals cosine negative 30 degrees. Okay? A little bit harder because of the negative, but we know that cofunctions have this property where their angles add up to 90. So we add 30, theta equals 120 degrees. The radians is a little bit harder. They were just not as good with radians, but we're also going to have to deal with fractions. But radians acts pretty much the same thing, the same way. I forgot to point out over here, similar identities can be obtained for 90 degrees when you use pi over 2. The radian equivalent is pi over 2. And so when we do example 2c, and we see these two things are cofunctions, instead of saying those two angles add up to 90, we would say in radians, those two angles add up to pi over 2. And so it's really the same thing, it's just a lot harder to do in your head. I'm going to solve that equation for theta. So I'm going to subtract 3 pi over 4. But when we subtract fractions, I'm going to get a common denominator. So let's call this 2 pi over 4 instead of pi over 2. So let's just subtract 2 pi over 4 minus 3 pi over 4, and you can see that theta equals negative pi over 4. Down at the bottom it says these are periodic functions. And so what that means is if you added 360, you're back in the same place. Add 360, add 360. Or in radians, you add 2 pi, add 2 pi, add 2 pi, you're back in the same place. And so what that means is there's maybe more than one answer. Okay? Infinitely many possibilities are given. We just found one of those answers. Applying sum and difference identities. If one of the angles A or B in identities is a quadrantal angle, then the identity allows us to write the expression in terms of a single function. Okay? I find that students are not very good at this concept, even though you should be. Okay, remember the quadrantal angles are the ones that I said you all should know. Okay, quadrantal angles put us in these positions. Okay, and so if I said sine 90 degrees, I'm looking at the y coordinate. I'm looking at the y coordinate at 90 degrees. Sine 90 equals 1, right? Everyone should know this. Everyone should be good at this because we've talked about it kind of a lot. If I said cosine 180 degrees, everybody should know that I'm talking about the x coordinate at 180 degrees. That's negative 1. If I said cosine 270 degrees, go to 270 degrees, the cosine is the x number. Cosine 270 degrees equals 0. We should know all of these. Okay? We should know these quadrantal angles. They should be quick. Okay? It's not difficult. It's probably the easiest concept of the day, but I find students, they're kind of weak at this problem right here in example 3. Write cosine 180 minus theta as a trig function of theta alone. Okay? So you look at this, and you're like, well, I don't know how to do that. But you should notice a pattern here that we see. Okay? That's a cosine difference formula. And the cosine difference formula, if you need to go back and look at it, go back and look at it. The cosine difference formula says cosine cosine plus sine sine. Cosine cosine plus sine sine. So it's going to be cosine 180 cosine theta plus sine 180 degrees sine theta. Okay? Just use the format, use the form that's given by the cosine difference formula. Difference formula. Okay? Cosine minus. Okay, so cosine 180. We ought to know cosine 180 from that picture above, from that circle above, the unit circle. We know cosine 180 is negative 1. So we have negative 1, and we don't know what cosine theta is, but that's okay. Plus sine 180, we should know sine 180. What's sine 180? 0, right? Sine 180 is the y coordinate, is 0. So if I was going to clean this up, 0 times sine theta is just 0. That's going to cancel out. I have negative 1 times cosine theta, which is just negative cosine theta. Okay? Go back and look at the directions again and look at what it says to do. It says write that thing as a trig function of theta alone. So write a trig function of theta alone. That's exactly what I did. Negative cosine theta. Example x1, suppose sine s is 3/5, cosine t is negative 12/13, and both s and t are in quadrant 2. Find cosine s plus t. Where I would start is just notice this is one of our patterns. Cosine s plus t. Okay, cosine s plus t is that's cosine sum. And if you don't remember it, look it up. It's going to be cosine minus sine. Okay, so start there. Cosine minus sine. What you should notice at that point is that we've got 4 holes to fill in. 4 unknowns, basically. Wait a minute, no, they gave us 2 of them. Okay? They told me that sine s was 3/5, so we should be able to fill that in. And they told me that cosine t was negative 12/13, so we should be able to fill that in. Of the 4 unknowns, they gave me 2 of them, and I'm going to have to kind of clean up and figure out the other 2. Now, it drives me insane, the number of students that will just go ahead and fill in the other 2 holes. I have no idea what you're going to put in there at this point, but some students are just going to try and just put a 3/5 in there and a 12/13 or something like that, just because they don't want to do any of the work. There's a lot more stuff to be done here, and we need to figure out what's in. They didn't give you all 4 of those blank spaces. They gave you 2. You need to figure out 2. Okay? Now the good news is, you've done this before. Okay, you have done this kind of problem before, and you've done it kind of a lot of times. In chapter 5, we did this a lot. Notice they're talking about S in quadrant 2. So what I would do, and we don't have to do it this way, but what I would do is draw a picture of S in quadrant 2. You've got this angle S in quadrant 2. We form this triangle. We did this a lot in chapter 5. I'm drawing an angle in quadrant 2, but they tell me that the sine ratio is 3/5. And so since I know the sine ratio is y over r, I should be able to label 2 sides of my triangle, y over r. And since I have 2 sides of a right triangle, that is a right triangle, I should be able to figure out that missing side using Pythagorean Theorem. And so if you want to go, x squared plus 9 equals 25, squared of 3 is square root of 5. Subtract 9, that's 16. Square root is going to give me plus or minus 4. Okay, and notice where we are. X number is over there in that second quadrant, or where we are on the left side, that's going to be minus 4. Now maybe you recognize that as a 3, 4, 5 right triangle. That's a very common pattern that emerges. 3, 4, 5, but anyway. However you find that that missing side is negative 4. What I want to know is the cosine ratio. Looking at this picture, it's easy to tell the cosine ratio is negative 4/5. That's x over r. And so I know cosine s is negative 4/5. I can fill in that one hole. I don't know the other one yet, because the other one's talking about t. Sine t, okay? I need to know something about t. So I'm going to draw a different picture, okay? A different picture of t in the second quadrant. So pretty much do the same thing. We're going to have t in the second quadrant. Now notice what they gave me this time. They gave me cosine, and I know cosine is x over r. And so my x over r looks like that. And then I should be able to do Pythagorean Theorem again. Pythagorean Theorem is going to tell me y squared plus 144 equals 169. Subtract 144, so y squared equals 25. Square root, I'd get plus or minus 5. But notice where we are. In the second quadrant, we're upstairs. That's going to be a positive 5 value. Okay? And what I want to know there is sine t. Sine of that angle t is y over r, 5 over 13. And so I've got my 4th missing piece. I'm trying to fill in those holes, and once I fill in those holes, it's just about simplification. Okay? So once I've got all those holes filled in, I simplify. Negative 4/5 times negative 12/13 is 48/65. Minus 3/5 times 5/13, that's 15/65. We got 48/65 minus 15/65 is 33/65. And that's my answer. Okay? Cosine S plus T. We're talking about the second quadrant for S and T. Cosine S plus T is 33/65. Now, down at the bottom, they say those values of cosine S and sine T could also be found by using the Pythagorean identities. I think it's a little bit harder, but what we could have done, instead of drawing those pictures, what we could have done was said, all right, I want to know cosine S. So I would say something like sine squared S plus cosine squared S equals 1. Okay. They gave me sine S was 3/5. So if I squared that, that's 9 over 25 plus cosine squared S equals 1. When you subtract and try to solve, if you subtracted 9/25, you're going to get cosine squared S equals common denominator, 25/25. We're subtracting 9/25 to get 16/25. Okay? If I'm solving this, I'm going to take the square root of both sides. Square root of both sides would give me cosine S equals plus or minus 4/5. But then you're saying, oh, okay, wait a minute, we're in quadrant 2. S is in quadrant 2. And so in quadrant 2, I would know that cosine is negative. And so that's how I knew that was negative 4/5. I don't think most of you are going to want to do it this way. I think most of you would much rather draw the picture. I know I would. Okay? We've drawn this picture and we've drawn these triangles a lot of times. And I think it's I don't know, I think it's faster for most of us to do that. But what they're saying is if you want to use the identities, you can use the identities. It's the same thing, but we can say it's 33/65. Example 4a, find the exact value of sine 75 degrees. Okay, sine 75. We've never been able to do that before, but now we can if we use some of the numbers in the chart. Okay, pretty quickly you can see that sine 75 would equal sine 45 plus 30. You could switch it around, say 30 plus 45, 45 plus 30. Sometimes there's more than one way of doing it, but whatever. Sine 45 degrees plus 30, that's the same thing as sine 75. And so, if you don't know this formula, look back at it. It's a sine sum. Sine sum means we're going to have sine cosine plus cosine sine. And this formula right there. Okay. So maybe you don't have to memorize it, but it helps, I think. We have sine cosine plus cosine sine. Sine cosine plus cosine sine. Okay. And just use the chart. Sine 45, square root of 2 over 2. Cosine 30, square root of 3 over 2. Cosine 45, square root of 2 over 2. Sine 30 is 1/2. I don't know if you remember the last time we did this, the last example, it pretty much looks exactly the same. The numbers are almost always going to be close. Okay? When we clean up this fraction, we're going to square root of 6 plus square root of 2 over 4. Sine 75 degrees equals square root of 6 plus square root of 2 over 4. And you might be saying, well, last time we did cosine 15, and it was the same thing, but of course they are, because remember cofunctions? Those two are cofunctions. Cosine 15, sine 75, those are the same thing. So of course we got the same answer. Example 4b is going to be harder. Tangent is just hard, okay? So, 7 pi over 12, where's that come from? Again, look at your angles in radians and get a common denominator. So that's 2 pi over 12. That's 3 pi over 12. 4 pi over 12. 6 pi over 12. You can tell we can get 7 pi over 12 by adding 3 pi over 12 plus 4 pi over 12. Okay? So that's what we're going to go through. Tangent 7 pi over 12 is going to equal tangent pi over 4 plus pi over 3. These are reduced versions. Pi over 4 plus pi over 3 would happen to be 7 pi over 12. So, your pattern for a tangent sum, says tangent of the first plus tangent of the second over 1 minus tangent of the first one times tangent of the second one. Okay. So tangent pi over 4, got to look at the chart. Tangent pi over 4 is 1. Sine over cosine. Tangent pi over 3, square root of 3 over 2 over 1/2 is going to be square root of 3. So tangent pi over 4 is 1. Tangent pi over 3 is square root of 3. So looking at what we have 1 plus the square root of 3 over 1 minus 1 times the square root. Or 1 plus square root of 3 over 1 minus square root of 3. And I would love it if we were able to stop there, but we should know from algebra class that we're not allowed to leave a square root on the bottom. Okay? And so for me, the hard part is the algebra here. We have to rationalize the denominator, which means we're going to multiply by 1 plus square root of 3 over 1 plus square root. Okay. So foiling here, I would see 1 plus square root of 3 plus square root of 3 plus 3. And on the bottom, there's a shortcut, but the first time anyway, I won't use the shortcut. When I FOIL this, I'm going to have 1 plus square root of 3 minus square root of 3 minus 3. So the shortcut is that square root of 3 cancels out. Okay? So I'm looking at 4 plus 2 square root of 3 over negative 2. And I'm not really reduced here. I'm not allowed to leave that negative on the bottom, but I can divide everything by 2 and divide everything by negative 2. If you clean that up, if you simplify, 4 divided by negative 2 is negative 2, and 2 rad 3 over negative 2 is minus square root of 3. So there I have tangent 7 pi over 12 equals negative 2 minus square root of 3. Exactly. Example 4c, find the exact value of sine 40 degrees, cosine 160 degrees minus cosine 40 degrees, sine 160 degrees. You need to see this pattern. Sine, cosine, minus, cosine, sine. Okay? Sine, cosine, minus, cosine, sine. It should make you look at the formula, look at your formula sheet, and it should look like this one. Okay, you're looking at that pattern. It's all about pattern recognition. Sine, cosine, minus, cosine, sine. And so if that's the case, then you can see that A would be 40 and B would be 160. And so just kind of plug it into the other side of the formula. That means this. We'd have sine 40 degrees minus 160 degrees is sine negative 120 degrees. That's something we knew how to do back in chapter 5. Sine 120, we should have been able to use the chart, and skills from chapter 5, we know how to do this already. Okay? Now, one thing you might do is use one of those odd those negative angle identities, and we know that sine is an odd function, and so basically that means we can pull that negative out. I'd rather find negative sine 120 anyway. Negative sine 120. So remember how we do 120. Okay, 120 120 degrees puts us about right there. We look at our reference angle. The reference angle is how far off the x-axis. That's 60. So it's kind of like we're finding sine 60. I did sine 60. Sine 60 straight from the chart. That's square root of 3 over 2. Okay, sine 60 is square root of 3 over 2. But notice the negative sign difference. Okay. So anyway, if I was doing sine 120, sine 120 is like sine 60, okay, but it's in the second quadrant, meaning it's positive, so that's square root of 3 over 2. Sine 120 is square root of 3 over 2. We know that. We know that. But we've got this negative sign in front. It's negative sine 120, or the opposite of sine 120, so the opposite of square root of 3 over 2.